Okay, so hi everyone.
Word embedding? Yeah, like word embedding, image embedding, how would you change?
Hi. So welcome to this guest lecture. Today I will be giving you an overview of the field of data centers and cloud computing in general. We're going to basically cover a very high-level introduction to how these systems are designed. There's plenty of information on this topic. You can probably have full courses on them and so on. So this is just like a very, very simple introduction to things. Okay? And my name is Ahmed, by the way. You can call me with my first name. All right. So data centers, they are a new but also old concept. If you have ever heard about mainframes, computer mainframes, back in the days like 80s and 70s, people would have dumb terminals and there would be a very large computer room where everybody is just using his keyboard and monitor to do computations on these large computers. They have evolved. People went to personal computers, desktops, and workstations, but then people came back to data centers because they basically provide lots of benefits that people were interested in. So data centers are basically large server and storage farms. You have a building as large as this, sometimes much larger, where you just fill them with racks of computers, of servers. Okay? So many of them are as large as a football field basically, multiple stories sometimes. So they truly are huge. In 2014, Amazon has its yearly reInvent, where they actually said that on average, one of their data centers will have between 50,000 and 80,000 servers. Okay? And these are numbers from 2014. You have many terabytes or petabytes of data that are actually being processed on these systems, and this is basically why we want that very large computational power in the same place. They are used by many internet companies. Every time you go on Google, you're actually using one of their services. Facebook uses exactly that, and Twitter, and we can go on and on. Okay? It's mostly used for data processing, websites, and business applications, but now also for machine learning and artificial intelligence, right? So you basically have multiple usage for these data centers that are emerging. Traditional versus modern. So old data centers used to be static, where applications would run on the physical servers. You would basically have to actually install applications and stuff. You will have system administrators who monitor and manually manage these servers, many of them actually on site. And you will use storage array networks or network attached storage, SAN and NAS architectures for your storage system. Okay? People will realize very fast that this is very cumbersome. In most cases, you do not want a system administrator to be in charge of actually installing an application and running it and maintaining it. You want somebody who is actually seasoned in that application, so the machine learning person to actually run that application because he understands best what his application needs. So people started using virtualization. Okay, so most modern data centers, even if they are run by a single company, they will be virtualized. And there are multiple virtualization types. There's the VirtualBox virtualization platform that probably most of you have used at some point, I hope. But then there's KVM, there's Zen, there's Commu, there are containers, container technologies, there are container management technologies, and there's a whole field out there. Okay? So in modern data centers, you typically run your application inside virtual machines or containers. Okay? You have flexible mapping from virtual to physical resources. And this is the most important thing. You have increased automation that allows large scale. I'll give you a number. Facebook has a data center in northern Sweden, and they have 19 people on site. Okay? And that data center serves everybody in northern Europe. Okay? They have 19 sys administrators. So that's the level of automation you're talking about. And these are 50,000 servers. Okay? So this is the kind of automation that you want in your data center. You want basically to use less people, less of us, more of the computers to manage themselves. Okay? And this is the standard photo that people show when they talk about data centers. These are mostly Google data centers. They usually have their servers in blue light, very ambient, very nice. They look cool, right? So you have giant warehouses filled with racks and racks of servers, storage arrays. Now you even have GPUs. You have FPGAs, field programmable gate arrays, which are basically very versatile types of hardware that you can reprogram the actual hardware. You have every single computational thing that you can think of. You have now TPUs, for example, TensorFlow, the TensorFlow Google processing units. Okay? So you have all sorts of hardware packed and jammed into these large-scale data centers. And computations yield heat. Okay? So the cooling infrastructures of these data centers are just enormous. So, and you typically even try to automate the cooling infrastructures because they are very hard. Now, I just mentioned the Facebook data center in northern Sweden, in a small place called Modular. The reason that they put it there is that the average temperature any day is below 20 degrees Celsius, so they do not need cooling, right? So this is why people are starting to move things. Google has also bought in Finland an old paper mill, which they converted to a data center because what the way that they again cool their data center is just by pumping water from the sea on a hot day, which is like when I'm sorry, I'm speaking in Celsius, so probably many people don't understand. So the average temperature there is around 30 or 40 Fahrenheit, right? In that area of the world. So the water itself is very cold if it's molten, so they can use the water to cool their data center. And during the winter, they just need to open the window. Right? That's pretty much it. And actually, it's very cost efficient because many of these data centers, and when they put them in these very cold places, they will use this heat to actually heat buildings. So you kind of basically start getting every inch of power, every watt of power into your system doing something. Okay? Obviously, you have power converters and backup generators. Again, one of the reasons that they put their data center in that place in Sweden is that they have abundance of hydroelectric power. They actually have more hydroelectric power than they need. So there was just like this amount of electricity that no one was using, and they could tap onto it, and then they just wanted that. But then as all electric sources are unreliable, I mean, you might have, I don't know, for some reason, you might not be able to connect to the actual power grid. So you typically have backup generators that run on diesel to just like power these, or at least parts of it. Yeah? Modular, they are modular, and modularity here is on multiple levels. You have the servers themselves, which are modular. You have the server racks, where you just like put a bunch of servers. And some companies even use shipping containers. So if I need to add an extra capacity, I just need to have 1,000 extra CPUs here, or 10,000 extra CPUs here. I'm just going to take one of my shipping containers, move it on a truck, and put it in that data center. Okay? So it's very modular on multiple levels. You can add one server, or you can add a container worth of servers. This is not the standard. Not everybody is using shipping containers to move data. Microsoft, for example, they are even throwing containers in the sea, because then they do not need cooling, and there's abundance of area. They just like can drop their computations near people, just in the sea or the ocean. Now, you can easily add new containers, just like you add sort of your USB drive. You just add a container worth of computations, and you just need enough electricity to power these containers. Which basically means that today data centers are easily expandable. And since there is a very large need of computations in the world, everybody of us has, well, I don't have my phone right now, but everybody is probably running multiple applications which actually talk to a data center. You're running Facebook, you're running Netflix, you're running Twitter, and you're running Google, and so on. So there is a very expanding need for these computational powers. Am I talking too fast?
No.
Okay. No, because someone is transcribing, so I just want to make sure that. Yeah.
So for the companies that put their containers in the ocean, how does maintenance work?
I mean, this is still a research project. They have not still reached that point, but they have an ongoing research project, Microsoft research, and definitely this is one of the things that are very hard to manage. But almost all communication that you have right now is running through transatlantic and trans-Pacific fiber cables,
Sure.
Which basically means that you're already doing maintenance in the sea.
Okay, gotcha.
So I mean, it's still early work, but this is how the internet is actually running anyway.
Right. Cool.
Question. I'm still curious about how you do cooling with the containers, because it's huge. Because if they're like bare racks, it's easy.
I mean, you do not take like shipping containers as is and do that, right? What you're going to do is that you're going to redesign the container and open like a vent into it, have air and cooling. So there's a huge part of designing a data center is the aerodynamics of the system and the mechanical engineers out there. So when I was talking about the Facebook data center, they have like 19 people who are actually administrators, but I think they have like 10 or 15 mechanical engineers. Because you want somebody who actually manages that. So I mean, it's not as simple as let me stuff it in any container. Okay? And basically, server virtualization is at the heart of this like huge mega data centers revolution that we're seeing. If it wasn't for virtualization, it would have actually been, I mean, you would still probably use data centers, but not as large as we have right now. Because right now, you can just have like all sorts of applications running in parallel. So, and there are data centers that you do not even know that they exist. How many people here know about Akamai? Okay, most of the people. How much of the internet goes through Akamai data centers? 30%. So 30% of everything that you do goes through Akamai. Something that, well, everybody here is a computer scientist, so probably there's a much higher percentage of people who have heard about Akamai. But if you go to a layperson and ask him about Google, he will know what Google is, but he'll never know what Akamai is. I mean, nobody really talks about Akamai in press or anything, right? So you have these huge data centers that are everywhere right now. And virtualization is at the core of that, because Akamai is not running requests from a single user. They're running it from multiple users, right? And Google, right now, I mean, the cloud and so on, where people run, for example, the whole infrastructure of Netflix runs on Amazon, right? And other things run on Amazon also. So how do you do this kind of multiplexing? You need virtualization, which provides you with some security layer. So it allows a server to be sliced into virtual machines. You basically can divide any server in any way that you want. In most cases, obviously, and some with some sensible divisions. The virtual machine has its own operating system or applications running, so they are basically independent of everything else, except if you basically make them talk. You can rapidly adjust the resource allocations. Since it's a virtual machine, I can start a new virtual machine, add it to my cluster, basically effectively to the application, it feels like I've just added extra machines to that application, right? Versus if I'm just running on rigid computers, I will have to have a system administrator run with a USB stick to try to install things or install it over the network or something. And you do VM migrations within a LAN, so you can actually move a virtual machine from some place to some other place. Now, most people here, when we talk about virtualization, they will think about the common things. Right now, there are new virtualization techniques that are coming out. So, for example, AWS, Amazon Web Services, they just rolled out a system that is called Firecracker. And we have someone here who is an expert in Firecracker now, but that system can actually start 125 virtual machines in a second. It's the size of the virtual machine, or of the virtual, let's call it virtual machine, is 5 megs. And in doing that, people have been using things such as Alpine, Linux, Kata containers. There are many of these technologies right now that are actually trying to provide encapsulation, virtualization, with a very low cost for the users. Okay? And this is basically VM migration. So you have a virtual machine on some place and you just move it to the other place. Okay? So, as I was saying, virtualization allows for consolidated servers, because maybe you're coming up with this new application idea. Like, you just thought about, oh, I'm going to make a game that's called Pokemon Go. I'm going to roll it out. How many servers should I buy? Or maybe 10, maybe 100. I don't know how large would it be, right? Or maybe I'm the US president and I thought that, oh, I'm giving you Affordable Care Act and we are going to have a web portal where people can just log in and buy their insurance. But how many people are going to buy their insurance? Is it 10 million, 100 million? Is this even going to fly, right? So in these two examples, what happened is that people rolled out their service. The Affordable Care Act, basically Obamacare, got rolled out. People for months were not able to access the service because basically somebody miscalculated the demand and miscalculated how much computational resources they need, and it was rushed. There were multiple other reasons, obviously, but these were some of the reasons, right? Similarly, when Pokemon Go went out, people were not able to use it. There are multiple of these examples. So if you have this capability of having virtual servers where you can deploy them fast, you can consolidate them. So, well, if I come up with a new game that I'm going to call Ahmed Go, and I think that everybody will like that game, right? And then nobody likes it, I can just okay, shrink my virtual machines. I just want one virtual machine, right? Or I want 10 million. That's the idea. And then they are easier maintenance. Here's a nugget. Well, this is the sales pitch of data centers. Things are much more complicated. For virtualization, it makes life easier, and that's why people are using it, but it introduces other overheads. And that requires basically people like you to understand and learn and know how to use virtualization in data centers. Another way that people have been using it is that it's similar to the mainframe idea, the old mainframe idea where you would have okay, this is UMass has a bunch of people who are going to use their work computers. I'm just going to provide them with keyboards and screen, and then they can work. Similarly, people have been using the idea of virtualization to do virtual desktops, where you basically host employee desktops, virtual machines, and pretty much if you have a Chromebook, right, which is a very lightweight machine, in many ways it cannot do real hardcore scientific computations, you can still have virtual desktop on your company's servers and just log in and have a full computer that actually works. Right? So you get remote access with thin clients. Your desktop is available everywhere. Your work is available everywhere, and it's easier to manage and maintain. So the challenges that face people who are actually building these things, one of the main challenges is resource management. Because what you're doing is that you're turning multiple servers into one single computer, in essence. Okay? So you need an operating system for that computer. So how do I schedule? How do I schedule things? How does scheduling work? How does load balancing work? Okay, where should I put things? And all of a sudden, you have to consider heat, because you can schedule things and shoot yourself in the foot by basically having all your heavy computations in the same area, resulting in failure in your cooling system because, well, there was too much heat coming out of that area, and then all of a sudden, like having cascaded failures, that part failed, and then this part failed, and then that part failed, and all of a sudden, everything fails. And there's a very interesting thing there. I know someone who's running a data center at Ericsson, and he tells me about a guy who woke up and decided that he's going to update their software, the software that they actually use as the operating system for their Ericsson data center. And he, unfortunately, while doing that, was removing a file and did the famous sudo rm-rf/ on the whole data center. So I mean, this is something that is very mind-blowing. There is actually a thread on Quora where a guy who went and interned with, I think it was Dropbox, did a very similar thing. Okay? He brings Dropbox down. That guy brought, I think, banking services for like 10 banks in Europe down. And it's basically, I mean, and they basically, after that incident, they did not fire him, they brought him a cake and they made a party. Because it took them a week to bring back the services. So, I mean, this is what you get when you actually consolidate things, right? So how do you actually manage these resources? How do you trust your system administrator, but not fully trust him? Because he can really mess things up. And messing things up there is bad, okay? Versus basically him breaking the single computer. Well, I'll just buy a new one. So how to efficiently use servers and storage resources? How do I pack things? How do I make sure that I'm fully, I'm buying these huge amount of computations to run something, and I want to get every cycle for my buck, right? So, I mean, I really need to make sure that I'm fully utilizing these resources and right-sizing these resources. I mean, there is actually a scientific paper it's like a systems paper that was written by some people in Microsoft that basically says that nobody ever got fired for buying a new data center. Because you have this power now where you basically can just go to procurement, to the purchasing entity, and ask them, oh, I need 1,000 more servers for my data center. Because, well, I'm running very important workloads. But then it's much better if I can basically remove that purchasing order and just manage my resources in a better way. So that's resource management. And you have unpredictable workloads, so you might have, so people, I mean, you're here now, you're not using Netflix. You go home, there's a high probability that you guys are going to use Netflix, okay? So all of a sudden there's a spike in the number of people who are actually using Netflix. But in the same time, you're here if your company runs MATLAB on their local servers, like if they have MATLAB servers or if they have data processing servers, you're here at work or at studies, you're actually using these servers, but you're not using Netflix. So I mean, there are people using Netflix still, and there will be people who are working late still, but you have these moving spikes. Some spikes are not moving, so Michael Jackson dies and takes the internet out with him. You guys were probably too young at that time, but when Michael Jackson died, nobody could actually do anything. Internet was like broken because there was just a huge spike. Google thought that this was an attack on it. So they actually stopped providing services because they thought that, oh, this is a DDoS attack. This is distributed denial of service attack on my servers. So you can have these spikes, but they are not the most common kind of spikes, right? So how do you manage them? How do you differentiate between what is legit and what is wrong? Because how do you make sure that your resources are not being used because somebody is mining bitcoins on your resources? How do you make sure that someone is not using your service to basically make a DDoS attack against someone else? These are all questions. You want high performance and low cost, everybody wants that. You buy a phone and you want the cheapest phone and best phone, best camera on earth, but for $10, right? This is like our limit, right? So this is what people this mentality doesn't go away, right? So when you're trying to run a data center, you still want that. You want automated resource management. You want your 19 guys who are just running this huge data center to be able to basically, fault here, I'm just going to go and change something. And you want performance profiling and prediction. The amount of data that you log from a data center, you're logging everything. You're logging on the server level, you're logging on the rack level, you're logging on the temperature, on the cooling, on everything. So you want that. And you might even get some application metrics. So, I'm seeing spike, and so on. You want energy efficiency, because servers are they just eat power. Even if you're not running anything on these servers, they still eat power. You want to be green, and you want to save money. Well, you want to save money more than be green, actually. So there are reliability challenges when it comes to data centers. And these are basically your guy doing the sudo rm-rf backslash. These are the kind of things that you see. So typical failures in first year of a Google data center. 0.5% due to overheating. I managed to put all my workloads in the same area, and I have overheated the system, basically turning these servers, because the servers will just turn down. If they become overheated, they just turn down. They're not good. So you have a power down for most of your machines in under 5 minutes, and then you expect 1 to 2 days to recover, because right now that area is hot. How do you cool it? It's not like you're going to bring your fan and try to cool like a huge warehouse. So you need to really think about that. The power distribution unit failures. So you typically have a power distribution unit for each bunch of servers, typically 500 to 1,000. And then if one of these fails, you just get like 1,000 servers wiped out from your total capacity all of a sudden. One rack moves, somebody basically decides that, that rack doesn't make sense over here, I should move that rack over there. And that basically entails that you're taking out cables, and you're moving things, and resubnetting things, and so on. So you have plenty of warnings where 500 to 1,000 machines are powered down for about 6 hours. Right? One network rewiring, if you're basically... So one very, very hard thing to battle in data centers are rats. Rats love wires. And they eat your wires, and they cut your wires, and you need to run around searching for the rats and searching for where they cut the wires. You need to do pest control and all sorts of things. So a rat can actually bring your whole data center down. So this is basically you will need to rewire, because my cable is broken. What do I do now? I cannot just live with that. So rewiring, rolling 5% of machines down over 2 days span. Okay. You have 20 rack failures. 40 to 80 machines instantly disappear. 5 racks go wonky. Again, 40 to 80 machines disappear. Network maintenance, they have 8 of them. So 30 minutes of basically having connectivity issues within the data center, router reloading, router failures, 30-second blips for the DNS because you have like 80,000 machines that the DNS is trying to basically deal with them. 1,000 machines that just decided to fail together. Okay, they didn't fail together, but they failed at different times. Sorry, thousands of hard drive failures. Probability theory, which everybody loves in this room, I know, basically tells you that if you have 80,000 machines, you are 100% sure that you will get a failure. I mean, it's not about if I will get a failure, it's when will I get a failure. It's actually the probability is 1, or close to 1, that you get a failure within every, I can't remember the calculations right now, but probably every hour or something. And you actually need to run and do changes to these. So how much does it cost to run a data center? A whole lot of money. It's actually, I mean, these are old numbers actually. They usually capture the efficiency of a data center in PUE, which is basically the power usage effectiveness. How much power goes to actual computations versus how much power goes to basically cooling, lighting, and so on. All right? The typical is 1.7, which basically means that for each watt of cooling, for each watt of computations that you have, 0.7 watts goes to other things, which is a very large thing on your electric bill. I mean, green is nice, green is cool, but electricity is expensive. So if your efficiency, if you can reduce your electricity bill by 70%, you're very, very happy. Okay? The average Google PUE is actually 1.05 now, I think, the recent numbers, because they just started throwing their data centers in very cold places now. Okay? And these are very old numbers actually, but they just give you sort of an idea. And these are monthly costs. Okay? So you're going to throw out something like 5-10 million US dollars per month to run a data center. That's a lot. For 10 months, that's $50 to $100 million for running a data center. And if you have 42 of them, okay? So you're saving anything in this chart is millions and millions and millions of dollars. Right? And this is why some of the engineers, I wouldn't say many, but some of the engineers in the industry today make crazy amounts of money. Because if you actually improve my efficiency by 0.5%, that's hundreds of millions of dollars over the years. So I mean, if I give you a couple of million, I'm happy. It's a good deal. Why data center? Because of economies of scale. If you have ever had any course in economics, they usually tell you that if you buy, or if you have ever bought your own groceries, if you buy a single thing of anything, it's usually much more expensive than buying a bulk of things, right? So toilet paper, if you buy a single roll, it's probably 2 times more expensive than if you buy the 48 roll one, right? So it's the same for computer, and economies of scale are very, very nice to have in your system. So the larger the data center, the cheaper it can be to buy and run it, right? Because you buy equipment in bulk, you typically have these crazy agreements with companies, usually not just hardware companies, but with the electricity companies. So you go to an electricity company and you tell them, I'm getting 1 megawatt from you. How much are you going to charge me for that? And I'm like, yeah, I'm going to charge you like half the price of what everybody else gets charged, because you're basically helping me out, right? So you can make these very crazy deals, and actually cities and even countries are trying to promote themselves that way. They basically go to data center operators. Actually, I know that I refer to Sweden too much because I lived there for quite a bit. But they had a workforce, a task force, where I think 12 people were going to companies in many of these big companies, trying to convince them to get their data centers to Sweden, And in doing that, they would basically give them these, I'm going to make it much cheaper than the Germans. So please bring it here. Okay? Automation allows small numbers of system administrators to manage thousands of servers. So in a Google data center, Google has probably much, if you look at the percentage of software people versus system administrators, software people are much, much, much more. And the reason is that you have people who are actually working on the automation of the Google systems, or actually writing the software for that, to make sure that we need the least number of system administrators. Okay? So, general trends is towards larger mega data centers. There is an effort that is called the exascale computer, where they are trying to build exascale computers instead of the recent computer. But this is mostly for supercomputing data centers. So they want to build something that has exabytes of, not just petabytes of things, exabytes, whatever that means. So people are really trying to build big. And, well, data centers has helped grow the cloud industry, which is a pretty large part of many companies now. So, for example, Amazon. Most people on Earth would think of Amazon as this company that sells me stuff, right? But right now, a very large, profitable part of Amazon is Amazon Web Services, which is just selling compute resources to others. Okay? So, and many of these cloud computing companies, nobody really hears about them, like Salesforce and yeah. Well, there's one that, like Rackspace, yes. Very few people will know that a company called Rackspace exists. It's just not a brand, right? So it has provided many people with jobs also. So the central premise of this is that you want remotely available, pay as you go, high scalability, shared infrastructure. Basically, you want to be able to rent the amount of resources that you're using. And right now, the industry standard is that you pay per second. So after the first minute, for example, on Amazon, you pay per second. So you run the virtual machine for 120 seconds, you have some cost function, and you just multiply that by 120 with some add-ons, and you get like a month number. Okay? And people used to say that it's cheaper to run these systems, on these systems. It is not actually. It is actually usually much more expensive in the long run to actually run on the cloud compared to basically owning your own servers. Unless you're a company that does not really care about servers, like Netflix, because Netflix is not a company that even cares remotely about computer systems. Netflix is a company that cares about streaming, right? They want you to watch movies, so that's what they want, right? Okay. So there are many models for cloud computing: software as a service, platform as a service, infrastructure as a service. Infrastructure as a service is basically you renting virtual machines, specifying the size, specifying some capabilities, memory, you want a GPU on it, how many network cards do you want, and that is your infrastructure as a service. So you're sort of renting servers. Platform as a service, it provides you with more platform to basically write and run your own apps. So instead of, you're no longer renting virtual machine, you're renting something to run an app. Okay? And these are software, software platforms. And then you have the software as a service, which is basically, as the title says it all, you're renting software. So Salesforce is a cloud computing company that provides CRM software to companies, basically accounting and billing and such things. So it's still running on the cloud. You're still using shared resources. They open an account for you as a customer, but they provide you with that thing. Similarly, if you're been using Office 365, I think, software as a service cloud platform, because you can have, or if you're using Google Docs, you can have these very large docs with hundreds of megabytes. I mean, if you pay for them, they don't care, right? So you're actually renting resources and believing that they will take care of it.
Could you give an example of something you could achieve with the third that you could not with the second one?
Yes. So let me think.
Okay.
So for example, if you're Netflix, how do you provide streaming services on that system? Because you're building your own streaming software, right? You want to be able to manage where you put your videos, your subscriptions, and so on. I mean, you can argue that, well, I can run everything on here, I can try to develop everything over here, but it's just like the amount of control that you get. This is a virtual machine that gives you sudo. Basically, I can install anything, I can add any dependencies, I can do anything that I want. Versus this is something that basically provides you with a platform which is like, okay, these are the libraries that we support, these are the programming languages that we support, you have to use them. So it's, I mean, you can probably do everything here,
Right.
or most of the things, but still it's,
More flexible.
yeah, it's more flexible. So Amazon EC2 as for an example of infrastructure as a service. So it uses virtualization to share each server from multiple customers. So you can have a server that is actually divided. And they provide virtual CPUs. Do you usually take breaks in this class or not? Okay. Economies of scale, lower prices. Well, kind of. I'll tell you why now. You can create virtual machines with a push of a button. That is very true. And you can kind of calculate how much is the cost using some of the tools. They actually have the best tools out of all the other cloud providers, because they have been in the business. They actually started this business, kind of. Right? So they have lots of tools. So this is this will tell you how much is your monthly bill. And this is the smallest and largest machines that you can get. This is actually a virtual machine. This is bare metal. Okay? But you can look at this and basically say that, oh, you can get 12 terabytes of RAM for that much amount of money per hour, which in one day that's $600. Right? In 10 days that's $6,000, and in a year that's a very large number. Right?
I was going to ask, on the previous slide, you had Amazon and AT&T listed as infrastructure as a service. It seems like the examples are kind of dated. Like we're talking about Google App Engine, which I don't think exists anymore. But like,
yeah.
Is AT&T there because of like the telecommunications infrastructure they have, or do they? Because I don't think they
don't do cloud computing.
Yeah.
Yeah.
Well, I mean, they might have data centers and rent out space, but they are as well known on Amazon building something.
Yes, this is outdated. Yes. But this is not. Okay. So you can actually end up with, and then you get multiple storages. You can rent different bandwidth, and so on. Okay. Google App Engine, which is outdated. So this used to basically provide you with a way to write highly scalable execution platforms, where you basically, it's actually not very outdated because they do now support these languages. It's different from how it used to be.
They've like branded it into Google Cloud, which is like
Yes.
an AWS competitor now, essentially.
Yes, but it's on top of the Google Cloud, so it's
Still kind of.
yeah, it's still there. But it's just not as popular as it used to be. But to be true, it has never been popular. But it basically provides highly scalable execution platforms, must write applications to meet App Engine API. So you have an API that you must write your code against, and that API is available only for languages as of today: Java, Go, PHP, and Python. You cannot, for example, if you like something else, C, C++, does not support that. Okay. It has an auto-scaling capabilities, so it can increase or decrease the number of instances or the amount of resources, because there are no real instances there that actually that are actually run to support your application. It has strict requirements from the application state, so it must be stateless. Okay. It's not based on virtualization. Well, that's not entirely true, because it's running on Google Cloud and it runs on Docker on containers. So it's another form of virtualization, but it's closer to operating system level threading than like having a full virtual machine. And from the Google side, it allows Google to quickly increase the number of worker threads, which is basically the amount of resources, the amount of competing resources that you are getting. So one other model that people talk about a lot in the cloud domain is the public versus private model. So public clouds, Amazon, you can basically, me as a user, I can just go in and print something from them, right? Private cloud, Facebook, I cannot just go and do something on Google, on Facebook's data centers. They have it private for their own company. They run their own they run their own applications in there, and they control their everything, right? From the hardware to the application. So, if you're a company, you're usually faced with that choice. Okay. Basically, private clouds provides you with the ability of making sure that no one is sharing the same virtual machine, the same physical machine with you. Because one thing that you can do from a security point of view is that you can do side channel attacks. If there are two virtual machines that are co-located, there are attacks that try to infer data or read data from the other virtual machine on your virtual machine. So if you really care about privacy and such things, you want to run in a more private setting. That being said, you can actually go to Amazon and ask them for, I want that. You can write contracts with Amazon and ask them for, I want this 100,000 servers, nobody touches them except me. Right? So the US government actually uses AWS, and they do not share the things that they run with other users. Okay? And also one very big reason for private clouds, for example, there are many regulations, especially in places like Europe, where patient data, for example, and this is a very, very big thing in Europe, patient data cannot move even sometimes across like cities. So it can be very, very restrictive. So you still want the power of a private cloud, because you want to do this analysis on the patients that you have in the healthcare system and so on, but you want to make sure that everything stays within my data center here. Versus if you're just running on Amazon, while Amazon tells you, well, you're running on US East 2, but who tells me that I'm actually running on US East 2? Of course I can do, I can try to basically ping the machine and see the distance and so on, but still, there is no guarantee that Amazon will not move things unless I actually own the servers. They wouldn't mess with the US government, but that's another thing.
So most of these big companies don't actually care about privacy of users. So in a private cloud, even in the public cloud, is it common to have the data be encrypted in any way, or is it just raw? Because even if it's a private cloud, the administrators, for example, can still get access to the data.
It's the old question of how much performance you're going to trade for the privacy you're going to get. Because it comes back to I mean, even in my Ubuntu machine, this is not my machine, but my Ubuntu machine, I can encrypt my hard disk, right? I mean, right now, if you're an Ubuntu user, you can encrypt your hard disk. How many people use Ubuntu here? Or Linux, one form of Linux. Okay. How many people encrypt their hard disk? Oh, the 3 people. But that is not the most common thing.
I mean, I'm talking about things like if there's government healthcare data, for example.
There are laws that would make them encrypt data.
Right.
I mean, everything is subject to regulations, right? The public clouds do not care about private users' privacy because there are no regulations that would make them care about public privacy. But once you get regulations that make them care about public privacy, all of a sudden it becomes important and becomes the most important thing for us, right? So that's, for example, what the EU has done with the GPDR. Right now, you go to Europe and you try to access some websites in the US, and they tell you, oh, you cannot access it because you're in Europe, and GPDR wouldn't allow us to have you access that. Because they do not encrypt things, they don't keep your data safe in some way. And so, some of these are very dumb websites. So I was trying to access Western Mass News from Europe, and I got that due to you being in Europe, GPDR, we're not going to show you anything. So it's, I think the privacy part is mostly regulations, and this is what most countries are realizing now. So there are more and more tough regulations when it comes to how people do privacy.
Isn't dealing with encrypted data in a data center environment already kind of a difficult problem because you need to store the encryption keys safely and stuff like that? And obviously, like, the data needs to be decrypted at some point. It's not
Yes.
like you could deal entirely in your data.
Yes, but this is exactly the point that I was raising, which is basically how much performance are you willing to trade? You can't build a fully encrypted system. It's not like you cannot do it. I mean, there will be technical difficulties, but there are many systems that are fully encrypted. I mean, your phone, your GSM phones are encrypted, right? All your calls are encrypted. It's less data, so that you can do that, but at the end of the day, it comes back to the point where you actually ask the question, is it really is that data that valuable? And if it is that valuable, then you will just encrypt everything. Or if the government basically tells you, well, you have to encrypt everything, you will encrypt everything. But what's happening is that most governments actually want backdoors, right? So I mean, if the government is asking the company to open up a backdoor to be able to basically snoop on your data, then how do you basically convince the companies to not keep these backdoors? I mean, because these backdoors are going to be used by the companies and by others, so it's, yeah. Okay, so the private cloud might have higher costs because all of a sudden, especially for companies that are not in the business of clouds, they now have to hire technical people, computer scientists, to assist admins, mechanical engineers, cooling people, electricians, and so on, and pest control for that. So I mean, you get like this bunch of extra bucks that you have to pay because, well, but that is not my business model. That's not even what I'm doing for business. And then there's the hybrid model where you basically say, okay, I'm going to have private cloud, which is of that size, and if I need more resources, I'm just going to rent from Amazon or from someone else. Okay, so it's a hybrid cloud model. There are many programming models that are actually used in cloud systems. Okay, most common is the client server, where you have web servers, databases, CDNs. Okay, so that's like the traditional programming model. You have batch processing, and if you basically can consider also things such as machine learning and analytics as part of the batch processing pipelines that you have, analyzing large amounts of data, doing analytics on it and so on. And then you have MapReduce, which is it's for data-intensive computing. It's again another model that can be used for processing large amounts of data, and it has scalability built in. I think you're going to cover MapReduce in the course. I think it's not entirely sure. Okay, so if there are challenges, so I think when Amazon started with their cloud computing business, they had to really convince people that the privacy and security concerns that you have are not realistic. So the first barrier for them to actually get customers was, why should I put my data on your data center? Why should I trust you with my data? Once that trust was built, somehow, because on the other side, Amazon can argue that they can hire the best security people on earth, which your company cannot hire. So if you're a small business or an average size, or medium-sized business, even if you're Volkswagen or Volvo or Chrysler, I mean, that is not your business model. You're not going to go and try to hire the best security person to protect your data. Versus Amazon comes to you and tells you, I have hired that guy who's literally the best security person on earth. How about you bring your data to my cloud now? So that's but it is still a concern for many people. And basically, how do you guarantee isolation between client resources? And another concern is, how do you guarantee that the companies that host your data are not playing with your data? So I mean, that's another. So why should I trust Amazon, the company that made a business out of selling things for people? Why would Amazon not sell my data without me knowing, right? So how do you make this trust? Extreme scalability. How do you? That's basically what we've been talking about today. How do you efficiently manage 100,000 servers? Programming models. You're not going to program for 100,000 servers or 1 million servers, okay? But you're going to program for a lot of servers. So how do you do that? So there is an old paper above the clouds from Berkeley that 2010, I think, or 2009, they tried to state what they saw back then as the main things that would stop people from using cloud computing, the challenges that we need to achieve as a computer science society to actually have cloud reach its full potential. There are many workshops and conferences with papers coming out. There's just too much hype in that area anyway. So after cloud computing, by a couple of years, someone came out and said, oh, we have fog computing. Like, why not? Let's throw in more names. And basically the idea would be that you have mobile phones, you have cloudlets or edge servers near the users, and you have very large scale data centers and maybe a couple of data centers in between. Why don't we just make computations fluid enough to run on everything? And then there was like the super fluidity cloud, and there are all sorts of names that come every year in these conferences. But there's a lot of work that is still being done there. There are technical blogs for Google, now Google Cloud for Amazon. There are other technical blogs. There's one that's called High Scalability. If you are in distributed systems, if you like distributed systems, High Scalability is a very, very nice blog to go through. And then there's James Hamilton's perspectives that are interesting. With that, I thank you, and I'm opening the floor for questions. Or is it over? I don't know how long is the lecture. So.
There was a slide that had like all the problems that Google would see in like a first year of data center. Are you saying that those were the problems in like a typical data center today, like first year, or those used to be the problems?
So these are there's a very strong culture of secrecy in these companies. what company would like to tell you that these are my faults, right? So you learn about their faults like years later, and which basically means that most of the data that you get from these companies are either outdated or inflated or deflated, because it depends on the most reliable company on earth. They are not going to give you the most accurate failure numbers, but if they're trying to tell you as a computer scientist, oh, please come and join me because I have these tons of very nice technical problems, then they would basically report you some numbers. So I don't even know how do we trust these numbers here.
So for supercomputing clusters and cloud computing clusters, are there any difference in the operations?
So supercomputing clusters versus cloud computing clusters. Yes, there are multiple differences. The first is that the supercomputing environments are very well optimized for problems that they have been solving for the past 50 years. So basically the way that you run things is that you supply the supercomputing cluster with tasks and you get a quota as a user, and that quota is basically for you for some time that you run your computations. It's a closed model, but the software, the technologies that are being used, even the way that they optimize their supercomputers are very different. So for a supercomputer, for example, people would typically run at 100% utilization. Cloud people would tell you that this is our main aim, but nobody in reality would want to run at 100% utilization for a reason, because if you get a spike, then maybe everything will fail. Versus in supercomputers, you just send in tasks and you wait for them for a week, month, years, depending on how much quota you have been allocated. And then fairness is very different there. So in clouds, what you care about is isolation. And supercomputers, what people typically look at is basically how do you provide fairness to the users. So I have this whole university campus researchers who are trying to run their simulations and trying to discover like the next drug or the next gene or something. And in doing that, I have tons of computations to do, more than what my computer can provide. So how do I basically manage all these, making all scientists in this environment feel happy? Also, the kind of spikes that you see in supercomputing, it's very, very typical that right before major conference deadlines, you see spikes in university usage, because everybody now wants to finish his last experiment. Every grad student wants to finish his last experiment. That actually happens now on some of these clouds, but since the clouds are not just for academics, they're not just for running your simulations, your biology simulations, it's no longer the case. Supercomputers, you do not host web services. I mean, nobody hosts web server on a supercomputer. I have not heard of it, at least. Maybe there are, but it just doesn't make sense, right? So supercomputers are, you can think of clouds as a more general form of supercomputers, but they truly are not also, because virtualization, for example, is almost, there is a lot of reluctance from the supercomputing community to actually use virtualization technologies. They do use it, but not at the scale that you would think. There are many differences. Okay? I think I would thank you at this point, and yeah, it will. I hope that this was